In example 4 here, I'm actually going to ask you to take some time to see if you can understand how you would set up two integrals, a dx integral and a dy integral, to actually represent the surface area of the solid that's communicated here. So I'm going to ask you right now, try to pause the video and give yourself the chance to try to work through this just to see how well you're understanding it. And of course, when you hit unpause, you'll go through and see me actually set up each of these integrals. All right, so if I was going to go ahead and work on this, one of the first things again I would do is I would start to sketch out a rough picture here. Now what I know right away is that the biggest value of x that I can possibly plug in here for this radical is going to be 25, right? That's the biggest. Because if I plug in anything more, I start to get negatives under the radical. So I know that I'm going to have some sort of a curve that looks like this. But if I'm only working from 9 over to 16, then it's definitely the case that I have this portion of the curve, and I'm going to be attempting to revolve this portion around the x-axis. So if I was to try to get at least a rough sketch of this 3D solid, I would get something that looks like this. Here's my original curve. Here's maybe a mirror image duplicate. And I'm just going to go ahead and play a little bit of connect the dots. And there we go. So I have this surface area is what I'm trying to find. And hopefully you can see right away that your frustums are stacking horizontally, and so you would tackle this as a dx problem by default. Let's make sure that all of our conditions are met. So you could say, we see that y equals the square root of 25 minus x is definitely non-negative on the interval 9 to 16, and y prime, which would end up being negative 1 over 2 square root of 25 minus x. Notice I just have to use the power rule here with a little bit of a chain rule. That's where my negative's coming from. I can see this is only going to be undefined for values of 25 and larger. And since I'm not using any of those, I can say that this is continuous on 9 to 16. So my default setup as a dx question is underway. I know that I can go ahead and write this as my arc length piece there's my arc length, goes from 9 to 16, and in the front I'm going to need 2 pi, and then I'd have to measure the radius here. Notice again the radius is going to be given by my function, and so I'm going to go ahead here and put in my 25 minus x. Okay, so there's my starting setup. You might be surprised to know here that this is actually a surprisingly easy integral to evaluate, but it would require that you understand how you can multiply two radicals together. If I wanted then to set this up as a dy integral, just to see if things would be easier, I could start by first converting over my arc length piece over here at the back. Now to do this, I'm going to have to go up here and kind of change my function into an x equals form. Notice that that's going to give me something that looks like this, and so my x equals form is going to be x is 25 minus y squared. So of course then the derivative of that is going to be negative 2y, certainly continuous, and so I know I can go ahead and set this up. I'm going to have a negative 2y all squared. Notice I can find my bounds in the y direction. If I plug 16 back into the original, I get 3. And if I plug 9 back into the original, I get 16, which square rooted becomes 4. So here I'm going to have bounds that go from 3 to 4. If I have then my change happening up front, I'll see that I need to go ahead and replace the length of the radius, which used to be measured in this vertical direction. It's still measured in the vertical direction, but I just note that I can replace my root 25 minus x with y, since that's exactly what it's equal to. I actually think the second integral down here is much easier to evaluate. So if you had to pick one to evaluate, I'd choose the second one. But it might be beneficial for you to try to use the first one just to kind of see how it actually works. And of course, the full details of those evaluations are posted up in the notes in Blackboard.